Good morning, chemistry students. Here are your kind of corrections and going over ChemQuest 21, Trends in Size. Information about shielding. Figure 1 Bohr diagrams of boron, carbon, and nitrogen. In boron, we see a nucleus charge of +5. Remember, that's because boron has 5 protons in its nucleus because its atomic number is 5. For carbon, the nucleus charge is +6, and nitrogen, the nucleus charge is +7. The little circles represent electrons. Because the nucleus is positively charged, it exerts an attractive force on the electrons. However, the 3 electrons in boron's outer energy level do not feel the full +5 attraction from the 5 protons in boron's nucleus. Before the +5 attraction gets to the outer energy level, it gets partially canceled or shielded by the 2 electrons in the first energy level. So this canceling, the proper chemistry term is shielding. Therefore, to the outer energy level, it only feels like a +3 charge rather than the +5 charge from the nucleus. So what we're talking about here is this electron in the first energy level is going to feel a +5 pull from the nucleus because there's nothing between it and the nucleus. But when we get to the second energy level, because these first 2 electrons in the first energy level shield or cancel out some of that positive charge, these electrons in the second energy level are only going to feel a +3 because there's 2 electrons in the first energy level shielding. Consider the diagram of carbon. An electron in the outer energy level only feels a charge of +4 coming from the nucleus because the 2 electrons in the first energy level shield 2 of the positive charges from the nucleus. So again, kind of what we're saying here is this electron in the first energy level, it does feel a +6 pull from the nucleus because there's nothing between it and that nucleus. However, when we get to our second energy level, these electrons, any of the electrons in the second energy level are only going to feel a +4 because of the shielding of the 2 electrons in the first energy level, canceling out 2 of those positive charge pulls. Question number 1. How large is the charge that the second energy level of nitrogen feels from the nucleus? So again, kind of same type of thing. This electron in the first energy level, it's going to feel that full +7 pull because there's nothing between it and the nucleus of that atom. However, when we get to our second energy level, because there are 2 electrons in this first energy level that are shielding or canceling out some of that positive charge, the electrons, any electron in the second energy level is only going to feel a +5 pull from the nucleus because of the shielding of the 2 electrons in the first energy level. The person who wrote this said, nitrogen's second energy level feels a charge of +5 from the nucleus. The total charge of +7 gets weakened by the 2 electrons in nitrogen's first energy level. Question number 2. Why does the first energy level in each of the 3 above diagrams only contain 2 electrons? Remember, this goes back to our quantum mechanical model. In the first energy level, there is only 1 sublevel, which is the S sublevel. The S sublevel only has 1 orbital, which only holds 2 electrons. So again, remember that was that quantum mechanical energy, quantum mechanical model of the atom. Okay? So in every Bohr diagram we draw, the first energy level will only ever hold 2 electrons because it can't hold more than that because there's only that S sublevel with 1 orbital. Question number 3. how many electrons can fit in the second energy level of any atom, right? In the second energy level, there can be 2 sublevels. Remember, our number of sublevels is equal to whatever energy level we're in. The 2 sublevels are going to be the S and the P sublevel. The S sublevel only has 1 orbital. The P sublevel, remember though, has 3 orbitals. So that gives us a total of 4 orbitals altogether in the second energy level. And remember, an orbital can hold 2 electrons. So that gives us 8 electrons total. So again, every time we draw a Bohr diagram, okay, the second energy level may hold up to 8 electrons total. Number 4, how many electrons can fit in the third energy level? So we're in the third energy level. Now we can have 3 sublevels. So we can have the S, the P, and the D. Remember, the S has, again, 1 orbital. The P has 3 orbitals. And the D sublevel has 5 orbitals. Okay, so that gives us 9 orbitals total, each holding 2 electrons. So the third energy level can hold 18 electrons total. And again, that means every time we draw a Bohr diagram in our third energy level, the maximum number of electrons we can put in it will be 18. Question number 5. How many energy levels does aluminum have? How many electrons should be in each energy level? Right? So to talk about how many energy levels, remember that correlates to what row we're in. So here's aluminum. It's in the third row. That means it's going to have 3 energy levels. Okay. Now, remember that an energy level has to be completely full before we can put electrons in a new one. So the first energy level can only hold 2, so it's going to be completely full with its 2 electrons. The second energy level, we said, could hold 8, so it's going to be completely full with its 8 electrons. That's going to bring us to 10 total, 11, 12, 13. So the third energy level of aluminum will contain 3 electrons because aluminum's atomic number is 13 and it has 13 protons. That means it also is going to have 13 electrons. So number 6 asks us to draw a Bohr diagram for aluminum similar to those above. So again, we have a plus 13 in our nucleus because its atomic number is 13. Here are my 2 electrons in my first energy level. And again, I can only put 2 in my first energy level because that's all it can hold. 5, 6, 7, 8. There are my 8 electrons in my second energy level. Again, I can only put 8 in my second energy level because that's all it can hold. That means that I'm left with 3 electrons. So here's electron 1, electron 2, electron 3. Remember, it does not matter at all where you draw the electrons. So there's our Bohr diagram. Question number 7 says, explain why the second energy level of aluminum only feels a plus 11 attraction instead of a plus 13 attraction for aluminum's electrons. So again, if we kind of talk about this, right? This electron, the electrons in the first energy level are going to feel a plus 13 because there's no shielding, right? There's nothing between these electrons and the nucleus. When we get to the second energy level, there are 2 electrons in the first energy level. that are shielding or canceling out some of that nuclear charge, which means these electrons are only going to feel a plus 11 pull from the nucleus. Number 8 asks, how large is the charge that the third energy level of an aluminum atom feels from the nucleus? So when we get to this third energy level, we have 2 electrons in the first energy level that are shielding. We have 8 electrons in the second energy level that are shielding. Okay, so that means that we have 10 total electrons canceling out our charge. So our plus 13 minus the 10 electrons that are shielding means that that outermost pull is only going to be a plus 3. So question 7, the person who wrote this explained it this way. Aluminum second energy level feels a plus 11 charge. The plus 13 charge of the nucleus gets weakened to a plus 11 by the 2 electrons in the first energy level. Number 8, it feels a plus 3 charge. The plus 13 charge of the nucleus gets weakened by the 2 electrons in the first energy level and the 8 electrons in the second energy level. So information about charge and distance. As you know, opposite charges attract. Examine the following diagrams of charged metal spheres. So plus 3 minus 3, plus 4 minus 4, plus 5 minus 5. And notice how the length of the arrows between them. The attraction between the 2 charged metal spheres in each diagram is represented by an arrow. The metal spheres are pulled closer together in diagram C because of the plus 5 to negative 5 attraction is stronger than the plus 4 to negative 4 attraction in diagram B and the plus 3 to negative 3 attraction in diagram A. Electrons behave the same way as the metal spheres are depicted in figure 2. Consider the Bohr diagrams of boron, carbon, and nitrogen in figure 1. Recall that boron's outer electrons feel a plus 3 attraction from the nucleus. Carbon's outer electrons feel a plus 4 attraction. In question 1, you found that nitrogen's outer electrons feel a plus 5 attraction. So they're kind of saying this is like nitrogen, this was like carbon, this was like boron. The attraction from the nucleus to this outermost electrons, okay, was a plus 3. For carbon, it was a plus 4 pull, and for nitrogen, it was a plus 5. That was what we got kind of back here where we talked about these pulls, okay? The attraction between the nucleus and outer energy level determines the size of the atom. If the attraction is strong, the atom is small. If the attraction is weak, the atom spreads out and is larger. So remember, this is our strong attraction. This is our weak attraction. And what they're saying is this is going to be related to how big an atom is. If the attraction is weak, then that atom is going to be larger. And if the attraction is strong, it's going to kind of pull those electrons in and make that atom smaller. So question 9, which atom is larger, nitrogen or carbon, and why? So these were what we drew for carbon and nitrogen. Again, remember, we had a plus 6 pull for the electrons in this energy level, and we had a plus 4 because of the shielding of those first 2 electrons for the electrons in the second energy level. Here, our first energy level, it was a plus 7, and in our second energy level, it was a plus 5, okay, because of the shielding of those 2 electrons. So the question is, which atom is larger? Well, the attraction to the outermost electrons in carbon is only plus 6, and in nitrogen, it's plus 5. So this means that carbon is, or nitrogen we can say, is stronger because that pull is plus 5. Therefore, nitrogen is going to be smaller. because though that nucleus is pulling those electrons in that outermost energy level here, okay, in more tightly. So the question really though was which atom is larger, nitrogen or carbon? So it's going to be carbon is larger because the +4 pull is smaller than nitrogen's pull. Therefore, carbon is larger. It's not getting its electrons pulled in as tightly. The person who wrote this explained it this way. Carbon, because nitrogen's nucleus pull of the outer electrons is harder than carbon's nucleus. Therefore, nitrogen's electrons are pulled closer to the nucleus, making nitrogen smaller. Number 10. In a silicon atom, the force of attraction between the nucleus and outer energy level is +4 to -4. Using a Bohr diagram of a silicon atom as an illustration, explain in detail why this is true. Right, so silicon, when we look up its atomic number, it's 14. So +14. In the first energy level, I'm going to put 2 electrons because that's all that it can hold. In the second energy level, I'm going to put 8 more. Okay, so that takes me to 10 electrons total, which means I'm left with 4 electrons for my third energy level. And again, you guys, remember, it doesn't matter where you put the electrons. Now, the pull here, right? Here there's no shielding, so my pull for my electrons in my first energy level would be +14. In my second energy level, because I have 2 electrons in the first energy level that are shielding, right, my pull is going to be then only a +12 for those electrons in the second energy level. When I get to my third energy level, I have 2 electrons in the first and 8 electrons in the second energy levels doing some shielding. So that's 10 electrons total, so my pull here will be a +4. The person who wrote this explained it this way. By the time the +14 charge of the nucleus is felt by the third energy level, it has to pass through a total of 10 electrons, 2 in the first energy level and 8 more in the second. This decreases the +14 charge by 10 to a +4 charge. Thus, the attraction from the nucleus is +4. Number 11 asks us to draw Bohr diagrams for sulfur and chlorine. So sulfur, okay, has an atomic number of 16. So +16. 2 electrons in my first. 8 electrons here. 3, 4, 5, 6, 7, 8. That takes me to 10 altogether. So that leaves in my third energy level for there to be 6. 2, 3, 4, 5, 6. Okay, so there's my sulfur. For chlorine, it has 17 protons in its nucleus. So again, 2 electrons in my first energy level, 8 in my second, 3, 4, 5, 6, 7, 8. And that leaves me 7 electrons. 1, 2, 3, 4, 5, 6, 7 electrons for my third energy level. So there are my Bohr diagrams. Again, remember, it doesn't matter where you put electrons. Number 12 says, find the size of the charge attraction from the nucleus to the outer energy level for sulfur and for chlorine. So again, we're going to kind of go through each energy level individually. The first energy level is going to feel that +16 because there's no shielding. When I get to my second energy level, I have a shielding of 2 electrons, so we would feel a +14 in the second energy level. So when I get to my third energy level here, I have 2 electrons in the first energy level, 8 in the second, giving me 10 electrons total shielding. So 16 minus 10 leaves me a plus 6 pull for my electrons in my third energy level. Doing the same thing for chlorine. In my first energy level, I'm going to feel a plus 17 because there's no shielding. When I get to my second energy level, I have 2 electrons shielding, so the electrons in this energy level would feel a plus 15 pull from the nucleus of the atom. When I get to my third energy level, I now have the 2 electrons in the first energy level shielding as well as the 8 in the second. So that's 10 electrons total shielding, so that's going to leave me with a plus 7 pull for those electrons in the third energy level. Question B asks, which atom do you predict to be larger, sulfur or chlorine? So larger, remember, means that we have a weaker pull from the nucleus for those outermost electrons. So chlorine's pull from the nucleus is plus 7, sulfur's is plus 6. Because sulfur's is plus 6, I expect sulfur to be larger because it's only a plus 6 pull from the nucleus. Again, chlorine would be smaller because it has a plus 7 pull from the nucleus. Explain in detail your reasoning to part B. Again, I just kind of did that, right? The person who wrote this explained it. Sulfur has a weaker attraction than chlorine. Therefore, sulfur's electrons won't be held as tightly as chlorine's. 13. Notice and compare the locations of boron, carbon, and nitrogen on the periodic table. Now compare their sizes. So boron, carbon, and nitrogen are in the same period of the periodic table. They're in the same row. Boron is the furthest to the left. Nitrogen is the furthest to the right. Remember, nitrogen, of the 3 of them, was the smallest, and boron was the largest. Because, remember, boron's pull was a plus 3 in that outermost energy level. For carbon it was plus 4, and for nitrogen it was plus 5. And larger pull means smaller atoms. Okay. Do the same with sulfur and chlorine. So remember, for sulfur the pull out here was a plus 6, and for chlorine it was a plus 7. That made sulfur the larger atom and chlorine the smaller atom. There is a general trend in size as you proceed from left to right across the period. What is this trend? In other words, how do atoms in the same row of the periodic table compare to each other in size? Right, so what we're seeing here is as we go from left to right in a period of the periodic table, the sizes of the atoms go from large to small. So in general, we are decreasing in size as we go from left to right across the periodic table. So the person who wrote this explained it this way: as you go from left to right across a row in the periodic table, the size of atoms decreases. Again, remember, that's decreasing because the pull from the nucleus is getting stronger. It's pulling those electrons in more tightly, making the atom smaller. Oops. All right, some information, Bohr diagrams and the size of atoms. Examine the following Bohr diagrams of 3 atoms from the periodic table. We have atom A, atom B, and atom C. Number 14, give the name and atomic number of each atom from figure 3. So to figure out the atomic number, remember I need to count the number of electrons. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 electrons, which means I have 11 protons here. Here I have 1, 2, 3, 3 electrons, which means I have 3 protons here. And here I just have 1 electron, so I have 1 proton here. So now I know their atomic numbers. Okay, atom A was 11, atom B was 3, and atom C was 1. Okay, because that was how many electrons it had, which makes atom 11 sodium, using your periodic table. Atom B is lithium, and atom C was hydrogen. And we know that because sodium's atomic number is 11, lithium's atomic number is 3, and hydrogen's atomic number is 1. Number 15. Concerning atoms A, B, and C, what is similar about their location in the periodic table? Well, hydrogen, lithium, and sodium are all in the same group or family of the periodic table. Remember, group or family, that's the correct name for the column of the periodic table. So they are in the same column on the periodic table. In atoms A, B, and C, compare the force of attraction from the nucleus to the outer level of electrons. While in C, for hydrogen, right, this was hydrogen, our pole is just +1. There's no shielding there. Atom B was lithium. And again, in our first energy level, we have a +3 pole. When we get to our second energy level, we have a shielding of 2, so our pole is +1. Atom A, which was sodium. Again, my first energy level, my pole is +11. There's no shielding. When I get to my second energy level, I have the 2 electrons in the first energy level shielding, so I'd feel a +9 pole from the nucleus. When I get to my third energy level, I have 10 electrons total shielding, the 2 in the first and the 8 in the second, which leaves me with a +1 pole for the electrons in that outermost energy level. Number 16. Draw Bohr diagrams for neon and argon. So those are both, again, in the same group or family of the periodic table. They're in the same column. Neon has 10 protons, so it has 2 electrons in its first energy level, and it's going to have 8, 2, 3, 4, 5, 6, 7, 8 electrons in its second energy level. For argon, argon has 18 protons. So again, we have 2 electrons in our first energy level. We're going to have 8 in our second. 3, 4, 5, 6, 7, 8. And then here's my third energy level for argon, and it's going to have 8 electrons. 4, 5, 6, 7, 8 electrons. So there are my Bohr diagrams. Question 17 says, what is similar about the location of neon and argon in the periodic table? Again, they are the same group or family. Okay, we can also say they're in the same column of the periodic table. Letter B, compare the force of attraction between the outer level electrons and the nucleus for neon and argon. So again, in my first energy level, I'd feel +10 because there's no shielding. When I get to my second energy level, I have 2 electrons in the first shielding, so my pole is a +8. For argon, in the first energy level, that pole's a +18. In my second energy level with a shielding of 2, my pole is +16. By the time I get to my third energy level, I have 2 electrons in the first energy level and the 8 electrons in the second shielding. That's a cancellation of 10, and so that leaves me a pole of +8 for the electrons in the third energy level of argon. Letter C, using your answers to 15b and 17b, what can be said about elements in the same column and the force of attraction between their outer energy level and nucleus? So what you need to notice here is my outermost energy level for both neon and argon, the pull both times was +8. When I looked at hydrogen and lithium and sodium, the pull in my highest occupied energy level, or my outermost energy level, every time was +1. So what are we noticing? Hopefully you are seeing that in the same column of the periodic table, the pull from the nucleus to that highest occupied energy level, or that outermost energy level, the pull is always the same. In the first column of the periodic table, it's +1. In the 8th column of the periodic table, it's +8. So the person who wrote this explained it this way. Elements in the same column have the same attraction between the nucleus and outer level electrons. Elements in the same column have the same attraction between the nucleus and outer level electrons. So question 18, atom A is larger than atom B. The attraction between the nucleus and outer level electrons is equal in atoms A and B. So what other reason could there be for atom A's larger size? Propose an explanation based on the structure of atoms A and B. So we could say that atom A and B could be neon and argon, right? Because, okay, what we're saying here is argon is larger than neon. The attraction between the nucleus and outer level electrons is the same, right? We said that. Here's +8, here's +8. So they have the same force of attraction. So why is argon a larger atom than neon? Hopefully, right? In neon, we only have 2 energy levels, correct? Of electrons. How many energy levels of electrons do we have in argon? We have 3. So why is argon a larger atom than neon? Because it has 3 energy levels. Look at these as well, right? This is also true here. Here in hydrogen, I have 1 energy level of electrons. In lithium, I have 2 energy levels. Here I have 3 energy levels. Which atom is going to be the largest? Sodium, right? Because it has 3 energy levels, which is kind of like adding layers, like how an onion gets bigger and bigger as you add another layer of onion skin, correct? Okay, same idea is here. We're adding another layer of electrons, which is making our atom larger. So the person who wrote this explained it. Atom A has an additional level of electrons. Each additional level increases the size of the atom. So atom A has an additional level of electrons. Each additional level increases the size of the atom. So question 19, which is larger, neon or argon, and why is this atom the largest? Again, we just kind of talked about that, right? Argon is going to be larger because it has 3 energy levels with electrons, whereas neon only has 2 energy levels with electrons. So argon is larger. Argon because argon has an additional energy level. 20. In general, there is a trend in the sizes of atoms as you move down a column of the periodic table. What is this trend, right? In argon, again, small to large. Okay, and our other example back here, right, here's our small, here's our large, right? So the trend here is that as you go down the column, okay, the atoms get larger. Why does this trend exist? Explain the basis for the trend. Again, that's because as you're going down a column also means that the number of energy levels are increasing. Increasing the energy levels causes the atoms to be larger. So remember our trend that we came up with here was as we go from left to right, we get smaller. And as we go from top to bottom, we get larger. That's our trends for size. So 21 asks us to order the following list of elements in order from smallest to largest. So we'll look at these first ones with some red. Okay. So potassium, arsenic, and bromine. So here's potassium. Here's arsenic, and here's bromine, right? So this is a period trend because they're all in the fourth period of the periodic table. So the question was from smallest to largest. Bromine is the smallest, next it's arsenic, then it's potassium, because our smaller ones are to the right on our periodic table. For our second one here, okay, we are looking at phosphorus, antimony, and nitrogen. So here's my phosphorus, here's my antimony, and here's my nitrogen. So this is a peer or a group trend. And again, they want us to list from smallest to largest. Smallest is at the top. So smallest is nitrogen, next phosphorus, and then antimony. Letter C, we have sulfur, calcium, magnesium, and chlorine. So sulfur, calcium, magnesium, and chlorine, right? So this is kind of asking us to do a couple at the same time, okay? So we want to go from smallest to largest. So we definitely know calcium is going to be bigger than magnesium or sulfur or chlorine because it's in period 4 and the rest of them are in period 3. Okay, so we want to go, calcium is going to be our largest, which will be our last one that we list. Now, we go from smallest from left to right. So based on that, the smallest is chlorine, next is sulfur, then magnesium, and then calcium. So to kind of give you those, write out those answers here, right? For letter C, it was chlorine, sulfur, magnesium, calcium. Okay. For nitrogen, antimony, and phosphorus, it was nitrogen, phosphorus, and then antimony. And for potassium, arsenic, and bromine, the smallest was bromine, then arsenic, and then potassium. So I hope that helps. Have a good day. I'll see you tomorrow.